My name's Curtis Johnson, and this is my presentation summarising my MSc Computer Science and Artificial Intelligence research project, Word Embedding Algorithms and Convolutional Neural Networks in the Detection of Fake News. As Parker Rim put it, fake news continues to undermine public trust and democratic discourse. Studies such as Statista 2020 findings show that a lot of people struggle to identify misinformation reliably, and where manual detection is inefficient, natural language processing offers scalable solutions to that. One underexplored area is how different word embedding algorithms behave when integrated into a fixed architecture like a CNN. Historically, researchers focused either on traditional machine learning techniques such as SVMs, random forest classifiers, and linguistic features, or on deep learning architectures like LSTMs, GRUs, and hybrid models. All of the research for that is available on the screen at the moment. Convolutional neural networks have been applied to fake news detection, including TICNN and some headline-based models, the research for which is also available on the screen there. Across those, they have all received relatively good results. It's clear that early traditional machine learning did have some drawbacks, and that is what has led us to deep learning techniques, and there has been some development as a result of the deep learning techniques that has led to some slightly more accurate results. Across all of the work, there is one consistent issue, and that is that studies change multiple variables at once. They often use different data sets, different architectures, and they're not necessarily comparing attempts at word embedding algorithms and how they apply, but realistically just at kind of how we're approaching the work, whether or not we can get a consistent approach to those. All of those researchers have relied on some form of word embedding algorithm and natural language processing to get their results. Within this study, I'm going to be utilising 4 separate word embedding algorithms, 3 of them static and 1 of them contextual. Word2Vec is static embedding that captures semantic similarity through its co-occurrence within a corpus. Glove extends that slightly by applying that co-occurrence across the entire data set. Where is that within there, creating an overall matrix of those embeddings. Fast text operates very similarly to Word2Vec, but it includes subword information, which helps with rare and morphologically complex words, out of vocabulary words, that kind of thing. And BERT, which is the only contextual embedding model which was approached in this study, generates dynamic representations based on the surrounding text. It is bidirectional, so it covers forward and backwards within the text and creates that dynamic embedding matrix based on what the context of each word is. It's much more complex and much more sophisticated than the static embeddings that have been implemented. Now, when looking at the research gap, the literature ultimately lacks a pure comparison of embedding algorithms within a fixed architecture. There's a lot of discussion of architecture, but there isn't really a lot of focus on the application of those specific algorithms within a fixed architecture and which performs the best. So the aim of this research was to build a consistent convolutional neural network architecture, implement within that the 4 embedding algorithms that were covered, apply those to an identical data set and compare their performance directly against each other where all other variables have been controlled. The methodology outlined within the research ultimately is to identify the dataset that we're going to use, and we'll come on to that slightly later on, pre-process that dataset, design a convolutional neural network, and we're using Python, and then implement into that convolutional neural network the 4 embedding algorithms that were covered again using Python, and then train that model using the CNN architecture that's in place. Overall, then I would analyse the results and determine from there where the research was going to go. All of the implementation was carried out using Python. Applications including TensorFlow, PyTorch, and Hugging Face were used. All of the local development was carried out on a MacBook Air M2, and Google Colab was used as the coding environment to allow me to tap into the GPU acceleration that is available within that. Across all of the models, hyperparameters were fixed. The CNN architecture remained entirely identical except for where certain variation was needed to implement the specific outputs of each word embedding algorithm, but the actual architecture itself remained the same. Gave us a fair and controlled comparison of the overall research. Now, the dataset that I selected for the research was the ISOT fake news dataset, primarily because of its size, but also just because of the consistency that it would offer. Consists of 44,898 articles. Around 21,000 of those were real and 23,000 are fake. It includes title, text, author, and publication dates. Now, whilst it is widely used within the research, it does have a few immediate drawbacks around it being almost exclusively political, focusing largely on the Donald Trump presidency. And it also only covers the area of 2016 to 2017, and I'll come on to how that impacted the research later on, but it is worth noting. Most of the real news within there comes from mainstream outlets, Washington Post, Reuters, that kind of thing. It doesn't necessarily have the same reflection within the fake news data set, which is mainly from sort of under the radar platforms, which may have syntactic and lexical differences that would need to be addressed within the research, and I will come on to that slightly later on. To start with the research, I focused on an element of pre-processing, which was taken from previous research carried out with the details of which are on screen, but an element of lowercase and punctuation removal, stop word filter and tokenization sequence pattern that was all applied uniformly across all of the static embeddings. As I'll discuss later on, this may have had a negative impact on the contextual embeddings, but the code for that is present on the screen at the moment. The CNN architecture is present on the screen. Ultimately, the overall design of the CNN isn't necessarily as relevant for the research as long as it is consistent across the different experiments that were carried out. The point of this is not to develop the most complex and applicable CNN for the real world. It's more about making sure that is consistent across the board. It was purposefully shallow. It was purposefully simple. All of the sort of output and everything that was used was all very, very clear why we were doing so. There was, as I say, there was only sort of 6 layers within that. Global max pooling was used to kind of capture all of that global co-occurrence that was available. A dense layer was applied with a ReLU activation function, and then a dropout layer of 0.5 to keep everything as sort of simple as we could across the board. The output was a sigmoid output, with it being a binary outcome. We were looking for either real or fake. Binary cross-entropy loss and the Adam optimizer were both used at their default hyperparameters because of their sort of storied use within this kind of context. All of the research was carried out over 10 epochs, apart from with BERT, which was given slightly longer just to give it a bit more of a chance because of its contextual nature to really build those algorithms. But other than that, everything else was kept entirely the same. There was an early stop and a callback implemented just to give us the best chances of getting that overall outcome correct. Now, the static embedding code is available on the screen. The way that they were implemented ultimately is the same across all of the processes. Those embeddings were taken, an embedding matrix was constructed, and then that was fed directly into the CNN for when that process went ahead. There were no real changes to that other than what was fed into those. All of them were 300-dimensional embedding matrices to keep that as consistent as possible, and that was then fed into the CNN. BERT functions slightly differently. So with BERT, CLS tokens had to be extracted from that, so we only ever used the final CLS token to feed into the overall CNN just to make sure that we weren't overloading that with information. It's not the most efficient way to use BERT, but it is a good way to compare it when you're building it within a fixed architecture like a CNN. The initial implementation highlighted a very clear architectural mismatch, which I will come on to, but ultimately this was the most appropriate way to implement that within the network, and the code for that is presently on the screen. So that in terms of the overall results, it was very clear from the results that the static word embeddings functioned incredibly well. The highest performer in terms of accuracy was and loss realistically was Word2Vec. The balance there was really good. The computational time was really good. Glove wasn't very far behind it, and fast text ultimately had a minorly lower accuracy and a slightly worse loss ratio. But ultimately they all performed really well, and the confusion matrices do show that. BERT underperformed significantly, likely as a result of the architectural mismatch, and ultimately the results for that was 73.75% accuracy with a quite high loss ratio. Although the computation time was a lot lower, it wouldn't be the best implementation for it, and I will come on to some explanation for that in just a moment. So in terms of the kind of overall discussion around those results, Word2Vec and Glove and fast text, they all performed really well, as I've just discussed. The simplicity of those algorithms, when coupled with a shallow CNN, do give us quite a lot of input there. They allow for a much more streamlined process to the approach to fake news. They're computationally efficient, they're very reliable, they likely would function very well on future data sets as well. The BERT performance was a lot lower, and as I've mentioned, I think that was a reliance on the CLS tokens. The pre-processing element of that also will have had an impact because BERT relies on a lot of the processing. The sort of word context is removed when it comes to pre-processing, so that may be ineffective with BERT. But for the purposes of consistency, it was left in place to make sure we were covering that off within the comparison. There were some additional models developed just for sort of insight more than anything else, and that aren't included within the results, where we dropped the dropout ratio, and where I also implemented removed the pre-processing, and BERT then performed a lot stronger with sort of 93%. So again, it highlights that architectural mismatch. The key insight from these results ultimately is that embedding choice must match the architecture. CNNs do excel at that local n-gram pattern, and static embeddings really represent that quite well. Contextual embeddings don't do so well with that, and they need a more transformer-based architecture or a hybrid design to help implement those more in place. In terms of sort of limitations of the research and future research, the ISOP fake news dataset, as I've mentioned, has drawbacks. It may not be as useful if we're going to apply this research to the real world, but for the purposes of this, it is quite useful because it allows us that consistency. But modern misinformation uses a significantly more evolved linguistic and stylistic style now than it had previously. Time has changed; those have changed. If we were to apply this in the future, that would need to be covered, and that artificial class imbalance will have played a role in the research as well. In terms of future research, we need to look at hybrid models which combine static and contextual embeddings to get the benefit of both of those. I think as well as CNN, which fine-tunes art architecturally to work with BERT, would likely be very useful as well. This realistically, this research only looks at text-based articles. Multimodal models which focus on images and text within a specific context may also be really useful, which would likely feed into that sort of hybrid model that we're looking at. And I think as well a larger, more real-world representative data set where the fake news presence is a lot lower would likely provide us with a little bit more insight into what we need to do with these CNNs to make them more efficient. But overall, as a sort of discussion point for what the research achieved, it did provide us with an overall outcome of which of those embedding algorithms functioned best within a CNN architecture that is fixed across all of the models. In terms of the overall sort of reflection on the research, it has deepened my understanding of natural language processing and convolutional neural networks, but specifically around embedding algorithms. It's challenged my initial assumptions that sophisticated models are always going to perform better, because in this case they didn't. I also learned the importance of architectural alignment and reproducibility within research to ensure that we were getting that covered off. We want to be able to create reproducible research so that other people can invest that as well. It also encouraged a lot of my technical challenge involvement. So initially all of the research was carried out in Jupyter Notebook, which just became insufficient for BERT. It's too complex and it's too large for that sort of computational demand, and I had to adapt and migrate across to Google Colab. In future work, I would likely evaluate datasets earlier and plan the computational requirements for that a lot more carefully. I think that early doors, it became clear that dataset was useful in this context, but if I was going to apply this wider, it wouldn't be so. But overall, the project, it strengthened my technical skills, my academic writing, and my ability to design and justify machine learning experiments. My knowledge of Python, my knowledge of the embedding algorithms themselves was really important. Planning ahead for specific outcomes also became a real lesson for me there. What will follow will be a small demonstration of the code operating. Now, because the experiments are across 4 different experiments, the code will be relatively short, but it will demonstrate the code running. Thank you very much for your time.